Hi, everybody. How's it going? Please let me know in chat if you can hear me well and you can see the screen and everything is all right. Okay. Okay, that's good. So yeah, so then I guess let's begin. As you all know, we have just recently released the update for Visual NAND Reconstructor, which is 4.2. We added several crucial options, especially for the memory chip reading and rereading with the ReadRetry and ECC features. Well, as all of you know, the nowadays devices getting larger capacities, and the chips are not getting better day by day. And we are with this particular update, we've been again laser focused specifically on like purification and perfectioning of these basically dump readings from the memory chip in coupled with ReadRetry and the ECC features. So this is basically one of sort of the biggest like amount of questions in support we have, the biggest amount of problems we have with this particular part. So we decided to sort of focus specifically on the problems that are our users facing daily. And we developed quite interesting features which I'm going to show you now. Well, first of all, we have added several quite a lot actually of new resources in this particular update. It's XOR keys, as always, memory chips and memory chip configurations, as well as new ECC codes for the newest devices and some old as well. There have been a couple of modifications of SanDisk XOR keys. They got slightly updated their keys, as well as several Silicon Motion, quite a newest XOR keys and ECC codes as well. We have, as always, we have added quite a lot of new pinouts this update, with several of them with the help of our users. So we can see people getting more and more familiar with pinout analysis on their own monolithic devices, such as micro SD cards and SD cards, and that's pretty good trend. We can see people buying logic analyzers and trying to analyze pinouts, and we always ready to help with that part as well, as some of you already know. So if you just have any problem with the signal analysis, you just send us waveforms and we will help you to find pinout. There are some conditions, of course, that pinout is going to be added to our database, but we can read them all in our guidelines in the help center. And so there's several micro SD cards, as well as most of those devices you can see pinouts for. They've been made for quite a high capacity. Some of them for the newest devices that we just purchased in shops. So it's like 64, 128 gigabytes devices, quite a high capacity, which is getting common nowadays. So yeah. So there are several, as I said before, several probably most interesting features in this particular update. We have added a new mode for ECC reading. Usually, I mean, I'm pretty sure most of you are already familiar with our tool. I hope so, at least. And you know that multi-pass reading of the memory chip is essential part of the data recovery process nowadays. So you cannot just, sort of like read the dump once, make correction, and be done with it. This is how it worked with older devices. Nowadays, you have to run ReRead through ECC map, of course, on the chip at least multiple times, at least 3 to 5 times. Normally, it's like 5 times is probably golden middle. So that's the amount of ReRead cycles we recommend for everyone. If you have any device with capacity higher than, well, let's say 16 gigabytes and higher, of course, depending on the quality of the ECC map, ECC correction results. So we have added a code word ReRead possibility now. So in all previous versions of Visual NAND Reconstructor, it's been the ECC ReRead have been the way that you read the whole page, right? So you have one page, it consists of multiple data areas which are protected by separate ECC codes usually. And so we've been attempting to reread the page until all of the data areas, all of so-called code words, we call them code words. It's just one data area protected by ECC. It's just one code word. So we've been attempting to reread a page until every single code word becomes green or correctable, you can say. Now, in this new update, we have added quite a very useful feature that helps to, it helps in the very sort of like bad situations when you have a memory chip which is really highly corrupted, and there is no way you can just read one page several times and fix all of the data areas at sort of like at one attempt. And there are many chips where it just doesn't simply work. And so in this particular update, you can selectively reread particular data areas in the page. So we kind of like split page onto like independent multiple areas which we can separately reread and correct it. And then on the next pass, if even half page is green and another half page is red, we will only try to fix and reread until another red part of page becomes correctable. We're not going to override anymore the green code words or green data areas. You can see here on the slide, that's where the option is code word, override code word, right? So it's been always override page by default, and now you can choose override code word. Normally, we would recommend to use this feature for the really like heavily damaged devices, specifically in scenario when you run normal read by page for 5 cycles or maybe 10 cycles, and it's not correcting everything. It does correct a lot, but not everything, and you still have this one page here, one page there, one page there, still uncorrectable. So this is when you want to try to use this option in order to selectively fix particular code words of the page. So, and basically, you can also see on the slide, this is how in the background, it's basically for the modern devices, of course, you would want to run this feature with the ReadRetry on. So you definitely need or want to use ReadRetry. And all our ReadRetry algorithms, they work this quite sophisticated algorithm that is running in the background. And this is how it looks from the inside, let's say. You can see on this picture a couple of attempts of reading with a different ReadRetry parameters. So on first try, we try to read and evaluate page one time, and then on some next try with another ReadRetry parameters, we read page another time. So we have 2 pages now on the screen. And as you can see, this little sort of cubics, they represent the one data area or one code word, you can say. And as you count, I would guess it should be 16, maybe 17 of them here. And you can see on the first attempt, we've got some, half or maybe more than half of the data areas correctable. And then second separate reread, we've got also most of them correctable, but as you can see now, there are some of them still red. And you can kind of see that if you actually take them two combined together, or not combined really, but just take green areas from one and put all together that is green, you should be able to fix majority of code words. Of course, you can only see here 2 attempts, and in many chips, when you do maybe 2 or 3 more attempts, like 5 attempts in total, let's say, you can have all of the code words are covered in green, correctable. So this is exactly like what's happening inside the ECC when you run ECC correction by code words. So it will simply override or fix just the green areas, and it wouldn't read them again. So it's quite a useful feature, which I'm going to show you how it works in coupled with some updated ReadRetry algorithm. So yeah, so this is what we have added to ECC correction. We have significantly improved these specific ReadRetry algorithms, which are one of the most popular, I would say, in all requests that we are getting to our support button. It's a ReadRetry 1, ReadRetry 2, ReadRetry 4. Most of them here are, actually all of them here are for, it's either Hynix or some SanDisk Toshiba chips. SanDisk and Toshiba is pretty much just the same chip, just labeled by different companies. So we improved significantly. This time we really significantly improved the Hynix and SanDisk Toshiba ReadRetry algorithms. And I'm going to show you now the case, the specific example, which is a very interesting one. Many of our users have been problems with this particular eMMC memory chip from the Tesla car. As some of you probably heard, like about a year ago, I think there was quite a big amount of large amount of cars made by Tesla Model S, I would say. They got a problem with computer when the memory chip was completely like worn down to the state when controller just wasn't able to fix the bit errors, and so the computer was failing, and the reason of that was specific eMMC, or maybe a couple of different models of eMMC memory chips. And inside this eMMC, which we normally do through eMMC NAND reconstructor, inside this chip, there is a Hynix memory. I would say quite a bad one, probably the worst choice for the high reliability applications. And because there are many many read cycles and write cycles, especially done to the chip during its lifetime, it's collecting a lot of problems in blocks, in pages. And specific specific problem was charge leakage. So the charges that are stored or infused into memory cells, they've been leaking out of cells during the time and usage. And so even standard controller that was used in eMMC memory wasn't able to correct errors. Many controllers, they store sets or like settings of ReadRetry inside the firmware, and usually in most of cases, not in most of cases, but in many cases, we can pull them out and basically look at what they're doing. And normally modern memory chips, particularly this chip, they normally just try to like 5 to 6 different settings of ReadRetry. And if it fails, basically they claim that page is unrecoverable and data is sort of like gone. The controller will just send you uncorrected data, which is pretty bad, of course. And so for this particular chip, we've been able to improve our algorithm to quite an, well, I would say extreme extent, comparing to even our previous retry was pretty, well, not ideal maybe, but it was pretty good. It was much better than controller actually uses for this particular chip, because as I said, the controller uses normally 5 to 6 attempts, and we use in the visual non reconstructor, we normally use, I would say, well, at least 300 to 400 maybe different values or sets in order to attempt to fix the page. So not on the page, but usually we work on the block scale. So and this particular update, this specifically ReadRetry 04 algorithm was improved the way that now it can fix well, maybe not 100% of errors, but I would say majority of errors, specifically in in critical areas such as the file system of device and files themselves, of course. So on the picture on the left, you can see how data looks without ReadRetry at all, just raw data from the chip. And you can see like majority of pages, they are simply read. Read page means ECC code is mathematically incapable of correcting the whole page just because it's too many errors. And the disadvantage of modern ECC codes is if you have like too many errors in particular code word or page, ECC cannot fix any of them. So if your amount of errors exceed the capacity of ECC, it's not like it can correct part of them and another part is not. So it doesn't work like that. It works the way that it either corrects all of them or none of them. So that's sort of unfortunate property of the BCH, specifically BCH ECC code. However, even with our old ReadRetry, with our previous version 4.1 of visual non-reconstructor, we've been able to correct well, not all, but majority of the errors in majority of blocks. And in the middle here, you can see how it worked with the old ReadRetry algorithm that we had from version, I would say 3.9 probably to version 4.1. And I have to say this chip is fairly popular from Hynix, not only in eMMC, but also in USB drives, SD cards, and I think some micro SDs as well. And so this is how it looked after 3 attempts with the old ReadRetry algorithm. Honestly, I mean, it was pretty bad, as you can see. Like probably like, I don't know, 20% or maybe 15 to 20% of pages, they are still read. Of course, if you run it for like 50 cycles, it would fix more, but not all of them. And now on the right here, you can see how we actually improved it, how it looks now. So keep in mind, it's only 3 ReadRetry attempts. So if you run it for, say, 10 more, 20 more attempts, it will most likely fix all of those read pages. Sorry. So now let me show you how it actually works on the real case, so you can see the difference yourself. All right. So here, let me show you case that I have. So you can see here the case, a specific case was extracted with the eMMC non-reconstructor just for purpose of showing you how bad the ReadRetry was and how good it is now. We have prepared like already solved case or corrected case, and here you can see original dump. The dump memory dump in original state, how it was extracted from the memory. And there are a couple of, we pulled out only 8 blocks. And you can see how badly the ECC map looks. So keep in mind, I didn't do here any rereads. So what we did here is we only corrected this dump. So just simply corrected what was possible to correct by ECC code itself. Now let me to demonstrate how old ReadRetry worked and comparing to how new one works. Let me demonstrate to you how what will happen if we run, well, let's say one or maybe a couple of maybe 3 attempts of reread using the old ReadRetry algorithm. So now let me open the so this shows the old ReadRetry. As you can see, the file data itself dated back to 2019. So here I'm gonna run it now. You can choose here usually how many pages you want to like test for ReadRetry. We used to have in the previous version like a value, I think it was 8. So this is basically amount of pages for which the ReadRetry parameters they're going to be adjusted. So we didn't really know. Well, usually, like in the previous version of software, if you set a couple more, like 2 or 4, maybe 8 pages, it would find like the most optimal value based on like the 8 pages. Now, as we change the algorithm and value choose an algorithm, basically, you can be good with just simply 1 page. I mean, you can simply keep it by default 1 page and run it, and it should be enough for choosing the best value for ReadRetry. So let me demonstrate to you this old ReadRetry and also new one in the new Codeword mode. So you can see like a couple of features at the same time. So now I'm going to run it for, it was set 5 cycles, but I think we can stop it at maybe 1 or 2 cycles. We will see efficiency of correction, and then we will sort of decide based on that. It certainly takes a little bit of time. The more pages set to test for ReadRetry, the more time it'll take. Depending on, of course, depending on usually processor, what we use for ReadRetry testing, and correction depends on the CPU or maybe GPU. If you use GPU for correction, we have added this feature, use GPU for ECC correction several days before, I would say. As you can see, it looks like this old ReadRetry works well. It's not bad at the first glance. It fixes at least half of pages. So keep in mind, we're testing it here on 8 blocks, so it doesn't look too bad. But let's see what will happen on second pass, or maybe, well, third pass if 2 wouldn't be enough. So we still have like 700 pages uncorrectable, and it's just 8 blocks, and it's 1 block is 256 pages, so it's not so much. It's about 2,000 pages in total. So you can still see out of 2,000 pages in total, we still have a bunch of pages here uncorrectable, like almost well, half, 655. So at this point, we can say efficiency of ReadRetry has, and ECC reread has dropped significantly, because at the very first pass we've been able to fix half, and now we're only fixing, I don't know, 5%, 7%, maybe closer to 10%, but that's quite a low amount of correction. And you can see third pass, it actually got even worse. So a third pass it's almost stopped to work at all, because it's like maybe 1%. Actually, it's actually much less than 1%. It's probably like 0.7% efficiency. So that's not very nice. Yeah, as you can see clearly, the map became better. I mean, it became significantly better, but in most of situations, it's still not enough. It's still not good enough to pull. Yeah, you can pull out at this point. You can probably pull out a lot of data, and a lot of data is going to be good. Not necessarily you will get file system working, because because in order to get file system fixed, you need to have really greenish map, and not like that, because right now we probably have, I don't know, 15 to 20% of pages still red, and that's pretty bad. And in this particular ECC, as far as I remember, we have eight code words. So this map is based on, like, it's showing you the worst out of 8 code words now. And so let's now switch to new ReadRetry that we and see how much we have improved this ReadRetry number 4. And yeah, so to do that, just need to because we updated resources and now it's basically it automatically connects to the newest version of ReadRetry here. So yeah, you still can choose how many pages you want to test. Normally, as I said, like by default, we normally go for 1 page, and it should be good. Override. Well, let's also use this Codeword mode. Actually, it tells you, like, use this mode only when you did 5 to 10 cycles, and you still have, you know, pretty average quality of ECC map. And this is what you call like average quality of ECC map. There's a lot of red here. I mean, it's much less than half, but it's still a lot. So that's pretty bad quality. And now I'm using the newest ReadRetry, which we have improved in the Visual Line Reconstructor 4.2 version. And let's see how it does, how it performs. I have to say the algorithm itself becomes like the parameter, the value choosing algorithm has become slightly slower, because there's a bit more logics working behind the scenes, but efficiency is it worth it. As you can see, I have specifically run this ReadRetry after we did 2 or 3 attempts of the old version. So this is not raw dump, but this is basically the, like, with a, let's say with a Visual Line Reconstructor 4.1, you'll only be able to you know, get results of previous results like we had. And now on the top of that, I have started the updated ReadRetry, which is now fixing, well, you can see yourself, it's fixing majority of the previously uncorrectable code words on pages. And this efficiency is still pretty good. I think it should be pretty good on the second pass, probably on pass 3 as well. Yeah, it's still correcting, well, maybe quarter or third of the data. If you keep it, usually for such a damaged chips, you can, of course, there's a limit. First of all, in some scenarios, some situations, if chip was significantly, you know, overheating, or I don't know, there was some electrical problems, whatever, you still can, you still can have those red and uncorrectable pages. But in majority of scenarios, you should be able to correct now this, most of Unix chips pretty good. And you can see still it's been a third pass now, and its efficiency is still good. It's still correcting like 30% on every single pass. So for such cases, I would recommend you to set. So we have default number of passes set to 5, because 5 is usually, previously we had 3. Now we decided to change it to 5 because chips getting worse, so it takes a little bit more attempts to reread and fix the dump. And so 5, I would say, is a sort of golden middle. This is what you have to go for by default. And if 5 is not enough, and you don't want to just sit and wait, you can always set it 30, 50 passes, and then just go do another job. And yeah. So it's been, I think, yeah, that's the last pass out of 5. Now it will only attempt to read this remaining 48 pages, 48 pages from the uncorrectable. Yeah, it's still working. So at this point, you can see yourself. There's some code words still, read, but keep in mind this chip was like it was horrible. It was like in horrible state, really. We can actually compare it just out of curiosity how the original dump was looking like before. So here we have so in this part we have already corrected both images as good as we can, and here you see original dump itself without correction. And if you just open them side by side, let me find some of the blocks. All right, let's open it side by side. So on the left side, we have original dump, and on the right side, we have corrected dump. So you can see yourself. I mean, look at this white stripe. That's a pretty distinctive place to check. You can see yourself. The original dump was looking just horrible. I mean, it was looking like something is just completely corrupted here. But in fact, the reason of that was just a charge leakage from the memory cells. As you can see, we've been able to fix it. And fix it to quite a great extent, I would say, and you can barely see any bit errors here on this particular white space here. So yeah, there's one you can see still, still remains. It was somewhere, but anyways, if you compare it, that's quite a result. Yeah, and so. From such state, which was like the dump was looking, completely destroyed. With this new retry, we got it to look like that, and you can even build file system of this particular device. Yeah, it takes a bit of time. So that was the real memory chip from the Tesla car. The chip was non-working, obviously through MMC. And I would say after probably, I think we said like 30 to 40 passes of ReadRetry, we've been able to fix pretty much everything, at least everything that was necessary to to pull out from this particular device. It's detecting the file system now. There are multiple partitions, so it takes a bit of time. Normally, from this chip from Tesla, people want to pull out the certificates, a couple of VPN keys that they want to extract. It's a fairly simple job now. As soon as you correct TCP properly. Yeah, so you can see yourself the file system and everything. Yeah, this is normally what people hunting for, is the certificate. Yeah, so here it is. All right, so that was just a quick review of what we improved with the existing ReadRetry algorithms, and of course, if you guys have some case where it doesn't work, or you still have a lot of uncorrectable pages, you can always drop requests to our support, and we can attempt to sort of adjust our ReadRetry, send the new file to you, and test it on your device. There's one more, and probably, well, in my opinion, most interesting, maybe second most interesting news in this update is completely new ReadRetry algorithms. As some of you probably heard, there are, well, and you've probably seen yourself, if you go to shop nowadays, you can buy 128 gigabyte device for probably, I don't know, $10, or I don't know, 10 euro, or maybe $15, whatever it is. So it's pretty cheap, right? And there's one particular technology that is growing fast now that basically enabled for the market to become, for the market to produce, for the companies to produce high capacity and cheap devices. It is a 3D TLC NAND memory. So it is not planar anymore. So it is not 2D when you have just like basically flat die or crystal of plane, which is connected to one CE and chip-enabled signal. And now they basically have this sort of sandwiches. So they put all the chips on top. You can find a lot of information in Google. Just Google for 3D NAND, and it's been a bit of a challenge with these devices because quality. Let me share you. Yeah, so the quality of the chips. Well, I mean, it's not horrible, but it's not very good, I'd say. You can see yourself on the picture how ECC map looks like when you just reread the memory without having ReadRetry algorithm. So for those chips, ReadRetry has become like a part of reading process. It's not just like optional thing. You actually have to utilize ReadRetry when you simply want to even like read the chip. On the top picture, you can see here you can see how spare area looks like in one of I would say probably Phison controllers. Yeah, I think it was Phison. How it looks without ReadRetry at all. So just a raw read, 3 passes of ReRead, just normal read, and it's all red. I mean, completely all pages are red because you can see yourself that they are literally destroyed. And this device is like not really the worst example probably of such the memory chip. The most common chips, or 3D TLC NAND chips on the market now, you can see them here. It is normally Micron or Intel. These are most popular, and there are also some of the Hynix memory chip, or Hynix memory chips that we that we already got in our laboratory, and we got several requests from our users regarding all these chips. And now, we're sort of glad to say that we can fix this. We can, fix ReadRetry. We can fix CCC on these devices, and you can, recover data from these chips. Again, the ReadRetry for those chips work quite well. As you can see yourself, that's a real result, and I'm going to show you a case now. This is how it looks. Specifically, this picture was taken from Hynix. It was a Hynix memory chip, the Hynix 3D TLC. And we got it after 3 passes completely green. So from this state to this, it took just 3 passes. Let me open the, let me connect the memory chip. And those chips, 3D NAND chips, we got we were getting some questions from users how this 3D TLC memory looks like, and whether we can read them or not in the visual NAND reconstructor. When yes, you can read them. They look just like normal TSOP. I mean, I'm pretty sure you don't see it here, but there's just TSOP memory. There's nothing really special about it. And let me show you the device itself. So that's basically the device. It's nothing really special. It's just a USB thumb drive. Yeah, it's a 3.0 interface, and it's got a quite a classic controller, I would say nowadays. It's one of the newest Ryzen controllers, and it's TSOP memory chip. So this 3D NAND memory, it's nothing really special from, well, physically it looks the same. By the architecture, they still use NAND protocol, which means there's not much of new in terms of connecting the memory and reading the memory. However, there's one thing they changed significantly is block size. So those 3D devices, 3D NAND devices, and particularly 3D TLC memory chips, they have significantly increased block size. On some of the Samsung and Hynix memory chips, you can see block size ranging from sort of like 700 to 1,000 pages. For Micron chips, they increase block size to approximately 3,000 pages. So roughly in terms of megabytes, we're talking here about 40 to 60 megabytes per block. You can see yourself, that's quite an increase, because normally in classic 2D or planar NAND memory, the block size was probably 4 megabytes, 8 megabytes, and nowadays it's like 60 or 40, 60 megabytes, and probably even more. So anyways, let's jump straight onto the case, and you can see yourself the result before ReadRetry and results after 3 cycles of read with ReadRetry. So I'm going to plug this particular chip now into the reader, so that's just the same reader as everybody has. And for these ReadRetries, you don't really need to do pretty much anything. For the chips that we support, we have attached the new algorithm. So when you just open ReRead, it'll automatically sort of offer you connect this ReadRetry to the ECC. So you don't need to do anything. Just run reread, set as many passes as you want, and it'll work automatically. Yep. So I've got a dump here, and I've pulled out several blocks. So in here we got. Yep. Let me share the case with you. All right. So now you guys can see the case. That's the, let's say, 64 gigabyte memory from the Pinouts. That's the configuration. It's about 600 pages here, roughly. And yeah, if you look at the data here, so here I've pulled out a couple of blocks through offset element, just to show you how bad it looks. This is files and controllers, so there's nothing special with page structure. It's a classic 1 kilobyte of data followed by, and then a spare follows. So, you know, on spare it's very easy to sort of like estimate quality of the dump, and you can hardly speak here about quality because it's so bad here that you can see it's basically you've got a couple of bit errors in every single, like almost every single byte. So this is completely unacceptable, and I can guarantee that you can like extract, or you can recover like 0% of data from here because it's all corrupted, all gone. And now, if we run normal reread without any ReadRetry, so you can see yourself how it works. Gonna run it in page mode. It wouldn't make any difference here. And I'm gonna set just one pass. So we have quite a large block size here. So it takes it'll take a bit of time. Normally for ECC correction, we do correct, like we prepare the whole block for correction. So we use sort of like buffering. So the larger block size, you have the slower status is going, you know, the map is going to update here. So yeah, it's not updated very often, and it'll be updated by sort of like large chunks at a time. All right, so as you can see, the reread has completed here with well, not very promising result, honestly. ECC by itself, together with reread, was able to correct, well, 0 pages out of 7,000 pages. That's pretty bad. Now, can just reopen it, and this ReadRetry is connected here automatically. Again, you can choose here how many pages you want to test. 2 pages, 1 page. Like, let's say by default you should go for 1, and if it doesn't find ReadRetry, or it's like its results is not so good, you can switch to 2, 4, 8 maybe, but it'll double time for testing every time. So, and the efficiency, like it's not guaranteed that efficiency will increase. So anyways, now let's set 3 passes here, and ReadRetry number 19. That's the one for the Hynix 3D TLC. Yeah, you see yourself, the ReadRetry analysis itself here is extremely fast. So we've been able to optimize to find specific range and optimize it quite well for the Hynix memory chips. You see like the Hynix, sorry, the 3D TLC is a kind of newish stuff. I would say they've been around for several years, but only now we actually started getting them in our in our laboratory. You can now easily buy them in the shops, and we started to get them, a lot of them, in our support department. So so that was the reason why we were laser focused on this particular research. However, I must say here that we don't have enough like history of 3D TLC. We don't have enough timeline of like analysis of the TLC chips. They've been around for, well, maybe a couple of years. So we got some samples here. They are like maybe 1.5 years old, and the charge leakage is a function of time. So the time passes by. Even when your device is just laying on the shelf, the electrons or charges, they are leaking out of transistors or memory cells. And it's not enough statistics now for us, just physically, because we cannot, wait for 5 years, let's say. There's no 5 years for now for 3D TLC. So we don't know exactly how badly they can be like damaged. So you can see on the picture it's pretty bad. It was like probably 1.5 years or plus minus after data was actually recorded onto the device. And our ReadRetry, it works technically and practically now quite perfectly on those chips. But if a couple more years or 3 more years passes by, we might need to slightly change settings of our ReadRetry and slightly increase thresholds of the charge detection. So we will be certainly like watching for these chips, and you guys send us, I'm pretty sure you're going to send us more requests for help with this particular chips, and we'll keep an eye on, sort of like in real time, we will sort of like keep an eye and test those chips like every couple of months to see if we actually need to improve the ReadRetry. So at some point, let's say what I'm trying to say, maybe after 1 year, a couple of years, we will have to go back to this algorithms and adjust them, change them. So if you guys have like any problems with the rereading, or your ECC map is not enough green, let's say, yeah, we'll definitely recommend it just to to contact us, and we can try to adjust ReadRetry and test it on your device. So the problem I'm trying to explain basically is sometimes we buy new devices, we buy damaged devices. So on new device, you can find the algorithm, you can test it more or less properly, and yeah, you can create the ReadRetry, and you can put it to update as we do. On damaged devices, you don't know how old they are, how badly they damage. Of course, when you get the dump, but those devices that are in the middle of sort of like lifetime is only you guys who have, because we don't have them. Like, we don't have clients coming to us every day, with like sort of like real cases. So we definitely would love to hear feedback, and always basically it's in our interest to help you, particularly with this part, to test our algorithms and to improve them based on your devices. Well, while I was talking, as you can see, we have finished ReadRetry when it's been only 3 passes, and as you can see, the very first pass fixed almost everything. Then the second pass fixed everything, and now we remained with a couple of bit errors. I mean, I'll just keep it as it is now. Of course, if you set like 2 more passes, maybe 3 more passes, it'll probably fix all of those. But that's pretty good result, I have to say. So now let's go back to the dump and actually check what we got in Sprayer here. Yeah, so you can see yourself, it's, well, almost 100% clean. There are a couple pages on the top which still are not corrected. That's probably those 2 pages which remained in ECC log. But if you run a couple more passes, it should do the job. So anyways, comparing to what we had before, again, let's just quickly compare it. That's quite a difference. Yeah, well, I'm comparing here 2 different blocks, but it doesn't really matter. Those are extracted from the same dump, so same chip. Yeah, as you can see, on the left one is what we got after correction, and the right one is before correction. So that how it was originally, the original state of the pages or charges in the pages. So yeah, that's now the Micron and Hynix. They have kind of similar algorithms nowadays for ReadRetry. So the same way it's going to work on the Micron memory chip. However, on Micron, it'll do probably slower because it will update results at least slower, because Micron, they have 3 times larger block sizes. So yeah, it'll do a bit slower. Yeah, guys, so if you have any pending cases, maybe on hold cases, you can always drop us some update, or maybe you can check these new algorithms on your pending cases or on hold cases. And yeah, if you have any problems, we will be happy to assist with that. All right. All right, guys. Thank you for your time, and see you in the next video at some point.